Hello everyone and welcome to a new lecture. So here we're going to talk about limits at infinity. Okay, so what does this mean? Well, basically the limits that we have had so far. So for example, if we have f of x equaling to x to the 2, okay, we were saying, or the limits that we were having was the limit of this particular function as x approaches a finite number. Suppose x approaches 2 or 3 or 4, okay, and we would find the limit easily. Okay, but suppose instead of having something like that, so instead of x approaching a finite number, suppose it approaches infinity. Okay, even though infinity is not a number, but suppose your x values get bigger and bigger and bigger and bigger. Okay, so for a particular function f of x, what happens to your function, okay, or what is the limit of the function as x approaches infinity, as x goes bigger and bigger and bigger? Okay, that is the whole idea. So limits at infinity, that is basically what it means. We are putting larger and larger and larger values into the function, and we are seeing how the function behaves. Okay, what is the limit of the function f of x as x approaches infinity? We can have infinity meaning positive infinity, or we can have negative infinity. So it is not just infinity, it could be negative or positive infinity. Okay, so to give you an example, suppose I want to find the limit of f of x such that f of x equal to 1 over x as x approaches infinity. And then we're going to test what happens to the limit of this function as x approaches negative infinity. Okay, so what does this mean? Well, basically, I want to know what the function approaches as I put larger and larger and larger values right here. Okay, so suppose I have x right here and I have f of x right here. F of x equals to 1 over x. Okay, so if I put 1 into the function, what will I get? Well, I will get 1 because 1 over 1 is just 1. What if I put 10 inside the function? Well, if I put 10 inside the function, it will be 1 over 10. It will be 0.1. Okay, what if I put 100? Well, it will be 0.01. If I put 1,000, it will be 0.001. If I put a million, okay, well, it will be 0.000001. Okay, so the larger these values, okay, so the larger these values go, the smaller f of x become. Okay, so you can imagine it. If I put very, 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 very large values right here, this value that I have right here, it gets closer and closer and closer and closer to 0. And you can imagine it. The larger it gets, the smaller this value gets. So it goes towards 0. Okay, that is very, very interesting. That's a very useful fact for us. Okay, so if I have the limit of 1 over x as x gets bigger and bigger, actually the value of this is 0. Okay, because the function goes towards 0 as this value of x goes larger and larger and larger. Okay, so that is about the limit of f of x such that f of x equals to 1 over x as x approaches positive infinity. Okay, what if I have negative infinity? What happens to the function, or what is the limit of the function? Well, if I just put a negative right here, what do you think will happen? Well, the same thing happens. As my values get smaller and smaller and smaller, my f of x gets closer and closer to 0. It starts with negative 1 and then negative 0.1 and then negative 0.01. It gets smaller and smaller and smaller. My f of x gets closer and closer and closer to 0. So on both directions, either if I have positive or negative infinity, okay, the limit of 1 over x as x approaches positive or negative infinity, actually it equals to 0. And this is very, very helpful for us. And you'll see when we solve problems of limits at infinity, you'll see how useful this is. So basically, that is what limits at infinity means. So let's go to Dismos and let's actually check this out. So this is our function, 1 over x. Okay, what happens? So let's see what happens if I put larger and larger values into x. Okay, so let me start right here. The x value right here is 0.36. As I get larger and larger and larger values into the function, so right here is 0.67, I will put larger values, watch the value of the y. Right here is 0.212, and right here is 0.17, and it's 0.146. As you can see, let's zoom out, the function gets closer and closer and closer to 0. as you can see right here, the x value that I've put into the function is 14.6. The y value that I get is 0.068. Okay, so the larger values I put into my function, the smaller f of x I get. That is why we say that the limit of f of x such that f of x equals to 1 over x as x approaches positive infinity, even though infinity is not a number, is not a value, but the concept of it is we are putting larger and larger values into the function. The limit approaches 0. Okay, we are getting closer and closer to 0. Okay, the same goes for this side. As I put smaller and smaller values of x, so right here is minus 5.2, and then it becomes minus 9.4, and then minus 14, and so forth. The smaller and smaller values I put into f of x, my y values become closer and closer and closer to 0. So right here is minus 0.047, and then 0.04, and then minus 0.3. If we zoom in, okay, what we will see is the closer and closer, or the smaller our x values become, this red line gets closer and closer to 0. Okay, as you can see, it gets closer and closer and closer to 0. Do you see it? Okay, that is the whole idea. So the limit of f of x such that f of x equals to 1 over x as x approaches positive and negative infinity, okay, what happens to the graph, or what happens to the function, is you get closer and closer to 0. That is why the limit of the function equals to 0. Okay, so let's go back to the drawing board. Let's see how we can solve problems that involves infinity. So example 1. Suppose I have f of x to equal to 3 plus 1 over x, and I want to find the limit of this function as x approaches infinity. Okay, what is the limit of this function? And before we proceed, all the limit laws that we have studied so far apply to these cases such that infinity is involved, so we don't have to worry. So actually this equals to the limit of 3 as x approaches infinity plus the limit as x approaches infinity of 1 over x. Okay, we know that the value of this equals to 0. Okay, that's given because the limit of 1 over x, or the value of y as x gets larger and larger, approaches 0. So we know this is 0, and this is a constant. Okay, the limit of 3 as x approaches infinity is just 3. So this is 3. So actually the value of this equals to 3. Do you see how easy it is? So this fact, meaning the limit of 1 over x as x approaches infinity, is very, very useful, and we're going to use it throughout these examples. So let me give you another example. So example 2. Suppose I have the limit of x to the 2 plus 3x minus 1 as x approaches negative infinity. Well, let's see. Here we have a polynomial. Okay, what this means, what does the value of y approaches as I put negative infinity right here, right here, and right here. And for right here, it's just, since it's a constant, we're not going to do anything, so we can delete this. Okay, so if I put negative infinity right here, okay, it will make every negative large number that I put right here to be positive. So this approaches positive infinity. Okay, it goes toward positive infinity. When I put a negative right here, okay, it will be 3 times a negative infinity. I'm going to tell you again, negative infinity or positive infinity, they are not values, they are concepts. Okay, what this means is when I put smaller and smaller negative values, okay, what happens to this? Well, it becomes negative. It goes toward negative infinity. Okay, but what do you think goes faster? This term that goes toward positive infinity, or this term that goes toward negative infinity? Well, definitely this one. Why? Because this one is squared. It goes faster toward positive infinity than this term right here goes toward negative infinity. Okay, so you could say that the result of this actually equals to positive infinity. So that's how you should think about it. If we have a polynomial like that, evaluate the negative and positive infinity when you are talking about the limit. You have to evaluate the negative and positive infinity into them and see which of them goes faster. And usually, the leading term determines that. Here, the leading term is x to the 2, okay? This one forces everything else to go with it. This one goes toward positive infinity faster. That's why the result of this limit is positive infinity, okay? Let me give you another example. So example 3, and let's delete all this. So example 3. Here we will talk about rational functions in these coming examples. We will see what happens if I have a rational function p of x over q of x, okay? And each of them, they have different degrees, whether the degree of p of x equals to the degree of q of x, or the degree of p of x is smaller or larger than q of x. And we will see why that is important. Okay, so suppose I have 2x to the 2 plus 3x plus 4 over 3x to the 2, okay, minus 1. I have this, and I want to find the limit as x approaches infinity. Okay, it's very, very important when you have a rational function and you want to find the limit of the function as x approaches positive or negative infinity. Take a close look to the degree of this function. Well, the degree is 2. This is the degree. Okay, how about the bottom function? What is the leading term in order to determine the degree of the function? Well, 3x to the 2 is the leading term, and 2 is the degree of the function. Okay, so when we have rational functions, we have 3 options. Okay, either the degree, so degree of p of x equals to the degree of q of x, okay, or the degree of p of x is less than the degree of q of x, or the degree of p of x is greater than the degree of q of x. We have these 3 possibilities, and by p of x I mean the function that is on top, and q of x the function that is on bottom. If the degree of p of x equals to the degree of q of x, or the degree of p of x is less than the degree of q of x, so these 2 options, okay? If we have these 2 options, what we're gonna do is we're gonna divide the top function and the bottom function by the variable with the highest or largest exponent. So for example, right here, degree 2, it is x to the 2. So you're gonna divide everything that you have right here by x to the 2. As simple as that, okay? Also, if the degree of p of x is less than the degree of q of x, we will do the same thing. What if we have the degree of p of x to be greater than the degree of q of x? Well, we're going to talk about that. So in this case, divide p of x and q of x by the variable with the largest exponent. So right here, the variable with the largest exponent is x to the 2. I'm going to divide everything that I have by x to the 2. So actually, this will be the limit as x approaches infinity of 2x to the 2 over x to the 2 plus 3x over x to the 2 plus 4 over x to the 2 over 3x to the 2 over x to the 2 minus 1 over x to the 2. I'm dividing everything by x to the 2. Okay, so what is the result of 4 over x to the 2? Well, we know that the result of the limits of 1 over x as x approaches infinity is 0. The same goes for this. Okay, so this is 0. What about this one? Well, this is 3 over x. It's just the same thing. It goes towards 0. How about this? Well, these 2 will go away. I have 2 left right here. And this one goes towards 0, and right here, these 2 will go away. So actually, I have 2 over 3. So this equals to 2 over 3. And this is the result. This is the result of, or this is the value of the limit of 2x to the 2 plus 3x plus 4 over 3x to the 2 minus 1 as x approaches infinity. What is the limit of this function as x approaches infinity? Well, it equals to 2 over 3. As simple as that. Okay? So when you have a rational function and infinity is involved, this is the rule that you're going to follow. If the degree of p of x is less than the degree of q of x, or the degree of p of x equals to the degree of q of x, then you're going to divide the top function and the bottom function by the variable with the largest exponent. Okay? And you can think of it this way. Just choose the leading coefficient. Okay? So right here is 2 and right here is 3. Just divide 2 by 3 because that's the way it is, and you get 2 over 3. So if I have, for example, example 4, if I have 8x to the 10 minus 2x to the 11 over 5x to the 3 plus x to the 11. Okay? So what is the leading term? Right here, this is the leading term, and right here, this is the leading term. Since both degrees are equal, then I'm just going to choose the leading coefficients. So right here is -2, and right here is 1. If I want to find the limit as x approaches infinity of this particular function, well, it's going to be -2. As simple as that. Okay? So let me give you another example such that the degree of p of x is less than the degree of q of x. That is case 2. So example 5. Suppose I have the limit as x approaches infinity of 7x to the 5 minus 8x plus 1 over 3x to the 6 minus 2x minus 5. I want to find the limit of this function as x approaches infinity. Okay, well, here the leading term is this one, and right here the leading term is this one. The degree of the function on top is less than the degree of the function on bottom, so I'm just going to use this rule. So basically, this equals to the limit as x approaches infinity. What is the highest degree? Well, the highest degree is 6. So I'm going to divide everything by x to the 6. It's going to be 7x to the 5 over x to the 6 minus 8x over x to the 6 plus 1 over x to the 6 over 3x to the 6 over x to the 6 minus 2x over x to the 6 minus 5 over x to the 6. Okay, we know that this goes to 0, this goes to 0, and this will be 7 over x as x approaches infinity. So this will also be 0. These two will go away. This will be 0, and this will be 0. So I have 0 over 3, which equals to 0. It's totally fine. Okay, the limit of this function as x approaches infinity actually equals to 0. Okay, so for case 1 and 2, use this rule. If you have a rational function and you want to find the limit as x approaches infinity, look at the leading term, okay, in top and in bottom. If the degree of the top function equals to the degree of the bottom function, or the degree of the top function is less than the degree of the bottom function, okay, in those instances, divide the whole function, each term in the function, more precisely, by the variable with the largest exponent, and then you'll get the limit. As simple as that. Okay? In cases, for example, such that the degree of the top function equals to the degree of the bottom function, you just have to bring the leading coefficients, okay, and then put them on each other. So for example, right here, if this degree was 6, then the limit of this function would have been 7 over 3. As simple as that. Or if this was 7 and this was 7, I would just bring the leading coefficients and put them on each other. The leading coefficient right here is 7, and right here is 3. It will be 7 over 3. Okay, so that is case 1 and 2. How about case 3? What if I have the degree of the top function to be greater than the degree of the bottom function? Well, let me delete this, and let's look at that case. The limit as x approaches infinity of x to the 2 minus 3x plus 4 over x minus 8. Okay, so actually let's make this one negative 2x minus 8. Okay, so as you can see, the degree of the function on top is greater than the degree of the function on bottom. That is case 3. For case 1 would be the leading coefficients on each other. For case 2, we'd get 0. For case 3, which is this one. So how can you find the limit of this function? Well, what we're going to do is we're going to see how the function behaves when we evaluate either the positive infinity or negative infinity into it. Okay, here, if this one goes to infinity, this term right here, x to the 2, this goes to positive infinity. Okay, this one goes to negative infinity, and this one goes to, this is just 4. Okay, so since the leading term is positive, then the whole function right here goes toward positive infinity. How about this one? Well, this one, it will go toward negative infinity, definitely. So positive over negative will give you negative. So the limit of this function as x approaches infinity actually goes toward negative infinity. And you can do it in another way. Choose the variable with the highest degree, meaning choose the leading term. See what is the variable, whether it's positive or negative. And then for the bottom one, do the same thing. Right here, we have a positive over negative. Okay? That's why the whole thing goes toward negative. If we have a positive over positive, meaning the leading coefficient is positive on top and positive on bottom, then the limit of the function as x approaches infinity will go toward positive infinity. Okay? It's very, very easy, very, very intuitive. So that is about limits at infinity. Let's go to the next lecture and let's solve some harder problems and use the idea of limits at infinity for asymptotes. Okay? So let's go there.